If side-side angle were a congruence condition, it would go something like this. If two triangles have a pair of congruent sides, a second pair of congruent sides, and a pair of corresponding non-included angles that are congruent, then the triangles themselves are congruent. But in Math Task 1, you should have shown that side-side angle does not hold as a general congruence condition, so this is false, it doesn't work. But in Math Task 2, you should have also shown that side-side angle can be salvaged because it does guarantee congruence in certain situations. In this video, we're going to dig into that a little bit more, and we're going to see that having congruent pairs of sides and a congruent pair of non-included angles actually does guarantee congruent triangles most of the time. It actually does it 85% of the time, as we're going to see. And so we will look at the exact situations when it does work and when it doesn't work. There are many ways to salvage side-side angle and make it a true statement, and the best possible way to salvage it, or the most general statement you can make that's still true in every case, is to talk about side-side angle as a pair of congruent sides, then a pair of congruent sides that are less than or equal to in length the first pair, and then corresponding congruent angles. And this is often denoted capital S, lowercase s, capital A to represent the fact that the second pair of sides needs to be less than or equal to the first pair. In Math Task 2, the sample solution includes an explanation of this. You can also see Hirschhorn 1990 for a proof, or I'm sure there's some other proofs online. But the gist of it, or the way that I think about it, is to imagine starting with a side length, then a smaller than or equal to side length, and then a fixed angle. And how many triangles can you make with that? Well, you can only make one because your first side is able to swing around anywhere it wants because the included angle is not fixed. We can swing it anywhere we want, but when it swings to hit the ray that's formed by the given angle, there's only one place that it's going to hit, so there's a unique triangle that you can build, which means if you have that given side length and angle measure, you're going to have congruent triangles. Now let's have some fun and think about this a little bit further. We're going to use the convention of the letter A being the first side, B being the side that's adjacent to the angle, and then alpha being the angle measure for the given angle. So now imagine that you're handed some A, B, and alpha as the measures for the side-side angle of some triangle. Yeshurun and K in 1983 laid out all the possibilities for the relationships that you can have between this given A, B, and alpha. So you could have it where A is larger than B, and that's like what we just saw above, where you end up getting one unique triangle, so that guarantees congruence because there's only one triangle we can make if A is larger than B. It could also be, though, that A is equal to B, and in that case you also get one unique triangle. Here's kind of a picture, but it's basically you get this isosceles triangle, and that's the only way it can work out. Now another possibility is that you could have A less than B, but still have A be greater than B times sine alpha. And what this inequality is doing is just making sure that A can swing around and form a triangle, but A is less than B, which means this is an ambiguous case. There's actually two possible triangles you can make where A swings and forms a triangle, but A can swing and form a second triangle. Since there's two possible triangles to construct with this A, B, and alpha, it's an ambiguous case, and so that's what disproves the general side-side angle. Now you could also have A less than B sine alpha. And in this case, your A is actually so short that it can't even reach the point that it needs to close a triangle. So if you have A, B, and alpha, your A is so short that it's swinging around, but it can't actually touch the ray that's formed by the angle alpha. So there's actually zero triangles that you can make. The last possible case is that A equals B sine alpha. So if you think about A equaling B sine alpha, what you really have is sine of alpha equaling A over B. So that means you have an actual right triangle. So that situation would look kind of like this, which means you do get one unique triangle. This one's actually basically like hypotenuse leg type thing. But the main point here is that there's one unique triangle that you can make. So to recap all the possibilities, we do have a unique triangle formed if A is greater than B, if A is equal to B, or if A equals B sine alpha. We have two possible triangles that you can build if it's the situation where A is less than B, but A is greater than B sine alpha. And then we have zero triangles formed if A is less than B sine alpha. Now, the cool thing that Yeshurun and K did was they actually theoretically determined the probability of having a unique triangle 2 triangles, the ambiguous case, or 0 triangles. So what you can imagine is, imagine randomly generating an A larger than 0 and a B larger than 0, and then imagine randomly generating some angle between 0 and 180, because it's got to be an angle from a triangle. So if you randomly generate those 3 things, you can determine the probability of whether or not side-side angle gives you a unique triangle. If it gives you a unique triangle, then side-side angle actually guarantees congruence. And what you would find is that a unique triangle is determined 50% of the time. So if you randomly generate those 3 things, 50% of the times they are generated in such a way that there's only one possible triangle. 9.08% of the time, it's the ambiguous case where you can build 2 different triangles. So you randomly generated an A, B, and an alpha, and you can actually use those to build 2 different triangles. 40.92% of the time, you can't make any triangle at all. So like your A side is just too short, and it's not going to be able to do anything, so you don't get any triangles. And these numbers were calculated theoretically, but also confirmed by simulations. 50%, 9.08%, and then 40.92%. So if you look at that, if you have side-side angle that are given, and if you're able to make a triangle at all, then 85% of the time that triangle was uniquely determined, and only 15% of the time was it ambiguous. So a student would actually be right in saying, well, side-side angle usually works. That's actually true. And then the more important thing here to take away is that the modified side-side angle with a less than or equal to second side always works.